Okay. After you have the data table and you have your graph of distance versus time, remember, once you get set up with your video on a computer and you can go frame by frame, this will be easier. Yeah, there are some things that you have to convert. You have to convert distance in squares to distance in centimeters. You have to get the times right. Once you get this data table, you know how to do a graph. The next graph you have to do is you have to do a speed versus time. Okay, speed. Okay. Make another column in your data table. And we're going to do delta t and delta d. All right? So to make room, I'm going to erase this. There's no delta in your first row where you haven't moved any yet. But if I want to know what the difference in time is for frame 2, then I look how much time has transpired since frame number 1. And the way I do that is simply by subtracting 16.2 from 16.1. And that leaves me with 0.1. If I want to know what the difference in time is for frame number 3, I just subtract the time at frame 3 from the time at frame 2. I'm just getting an interval time. In this interval between frames 2 and 3, 0.1 second has just transpired also. One more time. If I want to know what the interval difference is between frames 4 and frames 3, I look at the time at frame 4 and I subtract from that the time from frame 3. Again, it should be pretty consistent as far as the frame rate goes because cameras are designed to take so many frames per second, so each frame is going to have some fractional value of time. You get the distance, the delta d, the same way. So to fill in this box on your data table, look at how far you're at. Look at your distance and subtract from that the distance it was before. So 1.4 minus 0 is simply 1.4 centimeters. In the next frame, it went 2.8 centimeters total, but if you subtract from that the frame before, it went 1.4 centimeters again. So if you want to know the change in distance, you look at the distance it's at and you subtract from that the distance from before. Now, I think I made a mistake here. Let's see, 1, 2, 4, 4. This is to be like, something's wrong here. Anyway, if I'm going to stay true to what I just said, then this box right here, 4.2 minus 2.8, what is that? 4.2, 2.8. It's going to be 1.4 again? Okay, so good. Maybe I didn't get led astray here. I'm going to have to get my calculator.
It's right.
It's right? We're good? Well, now you'll have data for delta t and delta d. That's all you need to calculate speed, right? Because speed, or v, is equal to your change in distance over your change in time, right? So v for this interval is going to be the change in distance 1.4 divided by the change in time. If you do the math, what is that? 14 centimeters per second. And just because of the numbers that we're going to be using, delta d over delta t for this one is likewise going to be 14 centimeters per second. Delta d over delta t for this one is going to be 14 centimeters per second. This is a pretty easy one to graph. Because if you make a graph of speed versus time, at time equals, again, we'll go back to t here. At 16.2, we were going 1.4 centimeters per second. At 16.3, we were going 1.4 centimeters per second. At 16.4, we were going 1.4 centimeters per second. You see a trend here? It's going to constant speed, right? So when you graph that, your line of best fit is going to be a horizontal line, which means that your object was going at constant speed. Remember our d versus t graph. If you have the same t-axis, same time, what you would see is a constant slope, right? Where the slope of this line is your delta d over delta t, which is your velocity. So if it's a constant slope, then in your v versus t graph, it's going to be a horizontal line. Right? So then I'm going to ask you, when you write it up, that's going to be part 3. This is part 2. Okay. And I'm going to do that later.